within the scholarly realm. She is presently a fellow in energy and environment at also, similar to our first speaker, also has an affiliation with the Baker Institute, which is her where her fellowship is at the Institute for Public Policy. She has over 20 years of experience in industry, academia, government, politics, international relations, and managing waste operations. So this is, I'm sure she'll be speaking on this today, an emergency response to chemical, explosive, radioactive, and biohazardous materials. Her research focuses on issues of critical importance, such as plastic sustainability, domestic and international law as it relates to imports and exports and life cycle management of hazardous wastes, safety and environmental regulations related to the handling of chemicals within and outside the United States, and of course of clear relevance, coastal resilience of the energy industry. Similar to our first speaker, Dr. Melgar, Dr. Meidel has participated in public service that is impactful to her field. She was previously appointed as Deputy Associate Administrator of the Pipeline and Hazardous Materials Safety Administration here in Washington, D.C. That's where I'm sitting today, where she held the agency's domestic and internationally, or sorry, she led, apologies, the agency's domestic and international strategy, policy, and programs of hazardous waste materials on behalf of the U.S. government. Prior to this public service, she was the Director of Regulatory and Technical Affairs at the American Chemistry Council here in DC as well, where she represented the chemical and petrochemical industries in advancing a broad range of regulatory and policy issues. She has a doctorate in law and public policy from Northeastern University and several master's degrees in environmental chemistry and law, education, in applied science and technologies, as well as a number of important certificates relevant to science. She's going to be speaking to us today on an issue that one of our keynotes brought up, Marcia McNutt brought up, on circular economy, waste management, and the energy transition. So very critical for our discussion today. She'll be talking about policies and practices to enable circularity and sustainability. Dr. Meidel, I'll pass to you from here, and thank you very much for joining us.
All right, thanks everybody, and thank you so much, Sarah, for that introduction. And apologies on joining late. I wasn't able to hop on sooner. Today was the first day I decided to come into the office to give this, and ran into some technical difficulties here, so I apologize. And apologies for having my camera off. There's some bandwidth issues, and so I'll keep this off now, but I'll try turning it on during the Q&As. But yeah, so as mentioned, I'm going to talk about coming in at a little bit different of an angle here, talking about sustainability and some waste issues as we migrate into the energy transition. You know, right now, the energy industry is dominated by fossil fuels, but a number of environmental impacts and climatic issues have reached levels where we have to diversify and transition to alternative energies. But as we consider these new platforms, they come with their own set of challenges where we have to look at measures to ensure a sustainable roadmap that can better inform our decisions. So sustainability, we've heard this term so much and so often, it's become a buzzword, and it's used liberally, but it has so many different dimensions to this. Investors, consumers, and other stakeholders, they're really seeking now to understand what a company's risks and opportunities are, and to know about their performance related to sustainability. And so they're becoming aware of impacts such as overseas sourcing and waste disposal, and ensuring that suppliers and end markets uphold certain standards. So they're under immense pressure to account for sustainability, to meet global climate targets, and to integrate renewables and other low carbon technologies into their operations. And they're being driven by the market largely by shareholders and investors, by the UN Sustainable Development Goals and international treaties such as the Paris Agreement, and of course, consumers' personal values. Now, most people equate sustainability as having solely an environmental focus. So preserving future generations, attaining that sort of ecological equilibrium. But it's more than just assessing the environmental features. It's more than choosing these presumed eco-friendly options or switching to renewables. As our perspectives globalize, it's being seen for what it really is. It is a systems level philosophy, and a philosophy that integrates the environmental, social, and economic aspects. And there's a whole lot of subdomains, as you can see here, such as cultural, technological, and geopolitical. So it's the intersection and the equilibrium of those key factors. This is actually what sustainability is, and it has to be assessed from a holistic lens with a life cycle perspective. And how do decisions we make, so for example, to export waste overseas, to countries that may not necessarily have the capabilities and the technologies and the capacity to manage it, or the decision to integrate renewables, we don't really understand fully how something or if something can be totally recycled, or the decision to introduce untested biodegradable plastics into the economy. How do these decisions impact other parts of the value chain, both upstream and downstream, when the social, environmental, and economic factors are considered? So as our economy globalizes, it's even more critical that we find ways to account for all of the dimensions of what constitutes sustainability. So let me just give an overview here of sustainability and their goals. As I mentioned, there's a lot of pressure on governments and companies to align around these goals more than ever, and they're building these into their business models. So the UN Sustainable Development Goals, these are simply a collection of 17 different goals, and it builds off of decades of work by the UN. And what they are is they're a blueprint to achieve a better and more sustainable future. Corporate social responsibility, these are practices that outline how companies can effectively contribute to social, economic, and environmental accountabilities. And that's accountabilities to itself, to its stakeholders, and the public. Now, while CSRs are the effort and commitment to sustainability, environmental social governance, or ESG, measures the performance of the CSRs. And so these refer to the three central factors in measuring sustainability and the societal impact of investment of a company. And it's used by investors and shareholders to screen investments of their impacts to determine their future financial performance. Because nowadays, as we talk about sustainability, solely reporting on the economic performance of the company is just no longer sufficient for corporate investor decision-making. And for the world to meet these net zero CO2 emission targets, it's going to require a whole lot of infrastructure, a lot of land, other resources where the environmental, social, and other impacts are going to emerge, and many in developing economies along the supply chain. So that's why understanding where those impacts are and how the institutional context influences the sustainability across the whole value chain is going to be crucial for a fair, balanced, and equitable energy transition. So this is our current business model, which typically follows a linear economy, where we take materials, we make products, we use them, and then we dispose of them. And ideally, the goal is to gravitate towards circularity, where we design for durability, reuse, and repair, dismantling, but we're just not there yet. We're making some progress, but we're just not there yet. So this is the circular economy, and sustainability solutions and the energy dialogue, they revolve around this model. And it's gaining a whole lot of traction for achieving local, national, and global goals. And what this is a business model that keeps materials at its highest value throughout its life. It's an industrial system that's regenerative by design. So it replaces the end-of-life concept with restoration, and it aims for elimination of waste through superior design of materials, products, and systems. Now, most circular economy interpretations, they largely focus on landfill diversion and material looping. You see waste at each one of these segments, but these can result in trade-offs. So landfill diversion, this is oftentimes met by incineration or exporting agreements, and China's import ban exposed this common practice back in 2018 when they closed its doors to import waste. And although material looping can be effective, it's really only as good as the quality of the material that's integrated back into the supply chain. So, for example, plastics. I do a lot of work in plastics research. It can only be recycled once or twice before the quality degrades, and it's downcycled, and it's eventually landfilled, incinerated, or exported because it has an end of life. So it falls out of circularity. So more effort is needed into these areas, and these are methods for responsible extraction and upfront design and re-engineering so that materials at the end of life can be reinserted back into the economy with a second, third, or ideally an infinite life. Governments and companies need to build this mindset into their policies and practices, and we're just not there yet to the point we need to be to reach circularity and sustainability. Now, circular economy, it's a great vision, but it's just not a silver bullet for employment, sustainability, and prosperity. And it's really only attainable if the economic and the policy frameworks, the geopolitics, and all the sustainability issues that I mentioned can be achieved across the entire life cycle. So this is a simple life cycle flow diagram. And when we look at this, as a decision maker in business and policies, they're increasingly confronted with a whole lot of challenges in the search for sustainable solutions. And this is especially true as we face the current pandemic and we work our way through the challenges of the energy transition and we tackle global issues like plastic waste. We oftentimes look to policies, products, and technologies as solutions to help us achieve global climate and sustainability targets. So in this context, life cycle assessments, which look at impacts across the entire life of a product or technology, due to its systemic and cradle-to-grave approach at evaluating all of these impacts across the life cycle, this is important to look at it from raw material extraction to final disposal. And this will provide support in better integrating sustainability into decision making. And so apologies for the discombobulation, I suppose, of this slide. It's a basic life cycle flow, and this is for batteries. And for those of you that are well versed in the battery life cycle, I'm overly simplifying what is a very complex network, but policy decisions should be informed by life cycle assessments. I'll call them LCAs. And these catalog, as I mentioned, the environmental impacts across a product's life. However, when we look at the current LCAs, they're largely incomplete because neither the internal nor the external economic aspects are within the scope of current methodologies. And even the current ISO standard doesn't address the integration of an economic analysis. And it also doesn't consider any social impacts. Comprehensive life cycle assessments should be standardized, and it really should be an industry best management practice in order for us to achieve sustainability in the energy transition. So traditional life cycle assessments, they typically assess, as I mentioned, environmental impacts. Many of them are focused largely on emissions, but it really should include the full range of environmental impacts. So I'm talking about things like ecotoxicology and natural resources and biodiversity and so on. And these are important solutions, in order for solutions to be viable. Life cycle assessments results many times are grossly misinterpreted. When you look at some of the research that's out there, it paints a very different picture because so much of it depends on the scope and how far up and down the supply chain it's conducted. So are you looking at just the impacts of only the product manufacturing process? Or are you looking at the product manufacturing and the use phase? Life cycle assessments, and I'm not disparaging LCAs at all because they're very useful for identifying bottlenecks and deficiencies and creating all kinds of operational efficiencies within those boundaries. But it cannot be used to justify systems level sustainability or to guide any type of national or global policy decisions as it's currently being used in many cases. So for comprehensive insight into the impacts across the entire value chain, it's important that we look at each segment of the life cycle to assess all of these factors, while keeping in mind raw material extraction and end of life considerations. And these are two elements that are repeatedly overlooked, especially the end-of-life management for how something is actually treated. We don't really account for or have data for impacts to exporting or downcycling or littering or abandonment. So not accounting for these really provides only a partial picture of the true impacts from the life cycle perspective. Okay. So let me just give you an example of end-of-life oversight in a new energy technology and why standardized comprehensive LCAs should be required. So in here, this is a picture of a 200 kilogram Chevy Bolt lithium-ion battery pack. And propped up on top of it, at the left, is a postcard size pouch battery. 288 of these, of which make up a Bolt's battery pack. And for scale, you'll see a picture of a cell phone battery that is at the center and then an iPad battery at the right. Right now, 95% of lithium-ion batteries used for electric vehicles and smart devices are incinerated. Lithium batteries contain a ton of valuable metals and other materials that can be recovered and processed and reused, but there's very little recycling going on right now, less than 5% in the EU and the US, and much less in other areas like Australia. China's annual battery waste alone is already estimated to reach 500,000 tons at the end of 2020, and it's going to exceed 2 million tons per year by 2030, and globally, over 10 million tons per year of batteries will become waste. Now, lithium-ion batteries, they're difficult, they're costly, they're extremely energy intensive to recycle, and there's just so many technical constraints and challenges in disassembly, economic barriers, logistic issues, and a whole lot of regulatory gaps. And because the lithium-ion battery industry lacks a clear path to large-scale economical recycling, battery researchers and manufacturers have traditionally not focused on improving recyclability. Instead, they work to lower the cost and increase battery longevity and charge capacity. And because researchers have made only modest progress improving recyclability, relatively few lithium-ion batteries end up being recycled, which is why most of them are incinerated. The International Renewable Energy Agency in 2016, they estimated there was about 250,000 metric tons of solar panel waste in the world. So Irina, they projected that this amount could reach 78 million metric tons by 2050. Solar panels often contain heavy metals like lead, cadmium, other metals that can't be removed without pulverizing the entire panel. And so at the end of the life, solar panels are either exported where they're, or they're landfilled or incinerated here in the US or elsewhere. So today, recycling costs more than the economic value of the materials recovered, which is why most solar panels end up in a landfill. So there's also no, the other factor to all of this, there's no nationally or globally harmonized regulations for managing solar panels at the end of life, despite them meeting the legal definition of a hazardous waste. Waste management or the second life use is rarely considered in stages of development. And so this is, I guess, one of the points I'm trying to convey is that companies and governments, they largely don't contemplate this, including the ability for reuse or safety implications of repurposing when they're designing new materials or products or making materials more, which makes the materials much more difficult to manage and dispose at the end of life or recycling phase. And so this underscores an unquantifiable waste problem that runs counter to what the alternative energy and the renewable industry is held up to be, an ideal solution to combat climate change and an attractive investment for companies and a job creator for the US. So we have this glaring blind spot when analyzing the true environmental and social impacts of new energy technologies. Because what happens at the end of a product's life has a considerable influence on its overall sustainability score. So turning back to our LCA, what we're seeing is that at the end of the life, management of the waste is not really factored into the upfront design of the materials or products, and we focus more on the functionality during the service life and not so much on its end of life. And so this is, as I mentioned, gross oversight, and it's counterintuitive to any circular economy principles and sustainability. And upstream developments, as in the prior examples, are really not keeping pace with the needed downstream technologies and policies, such as recycling policies and the infrastructure needed, which leaves a massive gap in sustainability. So the greatest potential to steer technology towards sound, preferable outcomes exists at the earliest stages, and that's the technology development. We need to connect the energy sector with the waste sector and increase communication and coordination throughout the entire supply chain and incorporate recycling, disassembly, and reuse into the R&D. It really shouldn't be an afterthought, and that's the way largely in general, it's being treated now. And I'm not saying there isn't development and great innovation in the field of recycling of these technologies, but it's not scaled. And so that's why this entire LCA process is important, because it unveils barriers along the supply chain that are needed for a transition to be sustainable. So I want to move just quickly here to upstream activities in the life cycle and supply chain. The mining sector plays a really key role in the energy transition, as many of you know. The technologies required to facilitate the transition, including electric vehicles, wind turbines, solar panels, and improved energy storage, they all require significant mineral and metal inputs. And they generate waste throughout its life cycle, and they have impacts across the value chain, all data points that we need to collect. Critical minerals, as you see here, represent nearly half of the periodic table, but the United States remains heavily dependent on foreign sources. The Interior Department's reports in 2018 found that 31 of the 35 minerals designated as critical are import reliant, where the US doesn't have any domestic production and relies 100% on imports. And between 2014 and 17, 80% of the rare earth element imports came from China, while the remaining 20% was originally processed in China. And so China's been at this a really long time. They've been scaling up their mining capabilities since the 80s. And so this has resulted in an almost near monopoly on both the mining of the minerals and the processing of the rare earth oxides into the manufactured products. So this ushers in political and national security risks, sustainability risks, and trade risks, all other things that need to be quantified to really get a full understanding of sustainability. The map here displays reserve quantities of 18 of the conflict minerals. And the size of the circle here corresponds to the relative global quantity of the country's reserves, and that's overlaid with fragility and corruption measures. And so what you see are potential hotspots for increased fragility, conflict, and violence that results in growing mineral extraction across the world. And the geopolitics of conflict minerals is immense, and it's truly understudied in the context of sustainability, waste, and circular economy. Significant reserves of all of these identified minerals on the left here are found in states to be found to be fragile and corrupt. So how the minerals are sourced and how they're managed throughout its life, including the end of life, is really going to determine whether this transition supports peaceful, sustainable development in the countries where strategic reserves are found, or if it reinforces weak governance and exacerbates local tensions and grievances. Metrics such as mining and processing, smelting, trade, transportation, waste, and also the social, economic, and environmental costs are currently unaccounted for when determining the sustainability of the energy transition to renewables. We need to quantify those to understand how a technology or how a product that is being sold as a solution, how it behaves through its entire life and its impact on sensitive environments and populations. And also keeping in mind, what we may perceive as a solution in an OECD economy, a solution that may be technologically, economically, environmentally feasible, it may not necessarily be socially, politically, or environmentally, or even technically viable in another part of the world, especially in non-OECD or developing countries. So my point here with this next slide is all energy producing technologies have to be fabricated from materials and extracted from the earth. And so technically speaking, from this line of logic, no energy system is actually renewable, right? Since they all require continuing mining and processing of millions of tons of primary materials and then disposal of material at the end of the life. So absent any dramatic technological advances or an increase in the use of recycled materials, these inputs are going to come from the mining sector. And all forms of green energy require roughly comparable quantities of materials in order to build systems that capture nature's flows of sun, wind, and water. So in all three cases, the largest share of the tonnage is found in conventional materials like concrete, steel, and glass. And those are all very energy intensive processes. And further, mineral mining and processing is very energy intensive in and of itself, and it produces a lot of hazardous waste. And that's not to say that the waste and other environmental concerns can't be addressed and managed responsibly, but there's very little evidence of this occurring in China, where most of the world's minerals are being processed. Even if the metals are mined in the United States or elsewhere, China just dominates the entire supply chain And it's a very opaque supply chain. Most of the minerals or metals that are mined are shipped to China for processing. So we have to account for also those costs and the energy inputs of transport and processing and shipment back to the United States or wherever the materials or products are manufactured. And we also have to account for social injustices. Many of these countries I mentioned have very weak or absent environmental safety and labor laws, and they operate in very corrupt regimes. It's a very complex Byzantine and interwoven supply chain. It's one of the research that we're undertaking here at the Baker Institute, but this is why having transparency of life cycle impacts are essential to systems level thinking. So for many of the technologies and products deployed on the market, we just don't have insight into all of the risks and uncertainties and vulnerabilities on a systems basis. And the challenge for policymakers is to devise policy frameworks that enable the three critical goals of energy security, environmental sustainability, and affordability and access while the energy sector undergoes a fundamental transition. So if current forecasts are met, there's going to be over 3 million tons of unrecycled plastic turbine blades in 2050. And so, I mean, I'm just driving home this message here of how important it is to consider end-of-life management and upfront design of materials. And on the right schematic there, you can see that by 2050, under the current plans, the quantity of solar waste, much of it which is currently non-recyclable, is estimated to be 78 million tons, and it constitutes double the tonnage of all forms of global plastic waste that we have right now. And so it's something we have to consider, something we really seriously have to think about. So I would be remiss here if I didn't mention how the global pandemic has influenced the economy, since how we do business moving forward is going to be drastically changed. The pandemic has truly tested our resilience and highlighted our lack of preparedness and adaptability. It's also exposed a lot of vulnerabilities in our system. It's revealed shortfalls in our domestic production of critical goods. It's uncovered our reliance and enmeshment in offshore supply chains, and it's accentuated our dependence on foreign markets for end-of-life management of waste. So the way I look at this, in some ways, this whole crisis has raised the stakes for sustainability, and it's really become sort of a dry run for the sustainability agenda, and an opportunity for companies and governments to see how they can tackle an expanding range of challenges. Energy systems are frequently exposed to significant disruptions that affect economic activities, infrastructure operations, and society as a whole. Now, while many countries have made efforts to prepare for the health consequences of pandemics, not all countries and companies have yet given sufficient thought to preparing for the economic, humanitarian, and social consequences of such events. And so in the absence of these and effective planning, we'll encounter wider social and economic disruption and threats to continuity of services. So it's really important to see what are the takeaways of here and some of the lessons learned. And I think there's a lot to be learned from this, because we can really approach this pandemic with renewed interest and resiliency, and use this as an opportunity to build more sustainable business models while strengthening U.S. manufacturing supply chains. I think the supply chain disruptions are going to prompt brands to reevaluate and restructure and transform the dependence on global suppliers and find ways to reduce primary production by improving domestic waste management infrastructure and moving towards advanced recycling technologies. And we need to do this anyway. I think a potential longer term benefit from the pandemic is perhaps a faster pace of reshoring of manufacturing and investing in the design of circular materials. I think the more likely strategy will be building in redundancy in some of these supply chains rather than wholesale reshoring, because I think too much reshoring is going to make U.S. businesses less competitive and raise costs for consumers. But while this crisis exposes weaknesses in our operations, it really opens the door for investing in innovative engineering and advanced recycling, and for companies to make supply chains more transparent. We really don't have a lot of data, and it's shocking to see just the complexity of some of these supply chains. And so the way forward here, it's a systems level approach. The waste generated with new energy technologies It prevents an environmental challenge, but also we can also see ways where it can create value to pursue new economic avenues throughout the system. But before we can actually achieve circularity and sustainability, policymakers and industry and all the stakeholders really have to anticipate and plan for the massive influx of waste that's going to be entering the end of life phase, and design systems to capitalize on the resulting opportunities. And so that's in some ways adopting sustainable energy specific waste regulations for a renewable system, establishing end-of-life management policies to generate value and secure long-term benefits such as material recovery through recycling, and this will create new industries and jobs, creating end-of-life standards that are specific to end-of-life or to energy technologies. We don't have these right now. We need more data and analyses of projected waste streams at the national level to make informed decisions and help support the establishment of regulatory and investment conditions. And we also need regular reporting and monitoring of waste systems. That includes things with the waste produced by country and technology, the composition of the waste, the causes and frequency of system failures. There's a dearth of this information. We need to expand waste management infrastructure. And that's something that the pandemic and the China import ban really brought forth in our knowledge, is that we need to increase some of this. Strengthening domestic capabilities, adapting the unique conditions of each country and region, coordination mechanisms, this is one huge key takeaway, I think, is coordination between the energy industry and the waste sector. It's essential to supporting end-of-life management and to supporting sustainability in the circular economy, and stimulating investments in innovative financing schemes. And then always promoting ongoing innovation, R&D and skills development, and creating technologies that are coupled with prospective techno-economic and environmental analyses to maximize societal returns. These are things that we can do moving forward. So my last point here is that look, sustainability is multidimensional, and it's a critical investment for a just and informed energy transition. And it's more than just companies and governments switching to renewables. We have to assess the bigger picture here and be mindful of end-of-life considerations. With sustainability comes a huge responsibility. This commitment, a commitment to innovate, a commitment to supply chain transparency and its impacts across the life cycle, a commitment to strengthen domestic infrastructure and overall supply chain communication, a commitment from policymakers to design laws that are consistent and keep pace with technologies and innovation downstream, especially at the end of life, and a commitment to better inform our consumers. So as we journey through the energy transition with the goal of circularity and sustainability, we really have to ensure we don't unnecessarily complicate and confound existing systems, or shift risks, or create additional environmental or social setbacks. So all of this will be an essential element as the world transitions to a sustainable energy future. So that's the end of my presentation. I just want to thank you all for the opportunity to speak here, and I'm happy to take questions.
Wonderful. Thank you very much, Rachel, Dr. Meidel. So I'm just going to take a quick second to make a comment to the audience. Of course, in agreement with our speaker, the importance of recognizing the trade-offs and synergies with other SDGs is critical. So just to remind you all that to take this as a challenge, so not that we shouldn't be moving towards wind and solar, but how to figure out how to do so in the most sustainable fashion. Rachel, I'm going to start with a quick question, and while I do so, to remind the audience, I saw one question for Rachel, and there's one for the full panel as well. I teach LCA, and I'm an LCA practitioner, and so I kind of wanted to bring back to this whole notion of LCA always has to include everything all the time. Now, first, I agree with you. I think there's quite substantial limitations in terms of particularly end of life of renewables and batteries, because they're not well accounted for at this point, and they do pose sustainability challenges. And also reminding everyone that this is first step in solving a problem is recognizing it. So I don't see this as an Achilles heel. I see it as a challenge to all of us. But when we think through breadth and depth, LCA practitioners are still seeking, for example, a lot of my work is focusing on one impact and seeking to broaden our scope in terms of actually being able to account for supply chains from different countries. So how do you view the tension, or even limiting the scope in order for many other methodological advancements? And of course, this brings us back to the very origins of LCA, when there were questions, well, is it too early to standardize because there's still so much that can be done with the methodology? Clearly it wasn't, and ISO is extremely important, but I'm interested in your thoughts and comments on how to deal with this tension of how to manage improving the tool, which sometimes means the scope will be a bit more limited and focused. And of course, how we scholars do it is we really emphasize the limitation and what else needs to be done, with having a broad, comprehensive LCA that might mask or hide some of the potential impacts associated with energy decisions.
Yeah, and thanks for that question. And life cycle assessments, I wholeheartedly agree with everything you're saying. They're important to really understand what these impacts are. And you know, I'm not saying that they're not important, because they do create a better understanding of operational deficiencies and areas of improvement, and if within a certain scope of an LCA. You know, I think there are opportunities for improvement to, if we want to understand a system's, you know, the system impacts, I think it is important for us to gravitate towards more of a comprehensive life cycle assessment, and maybe not so much so with the ISO standards or others, but being able to concatenate data, to be able to aggregate the social impacts across a certain scope of a life cycle assessment, understanding what the economic impacts are with that, and understanding what the environmental impacts are. Because if we truly don't have a comprehensive picture and only a partial picture, I mean, how can we ever really achieve that equilibrium of sustainability? And so I do think there's work to do in integrating life cycle assessments, both from the life cycle costing and social life cycle assessments, which are something that's being thought of and conceived of now, trying to work them into current life cycle assessments, because, you know, we are a global economy, and so the things that we do here and the technologies that we develop here, I mean, there's system level impacts. It's never isolated to a facility really, or to a state or to a nation, because, you know, we're global in nature, and our trade and our products and our materials cross many boundaries. And so not to find a way to account for systems level impacts would not be would not give us a full picture of what's really happening out there. So so there is work to do to integrate these. I think there is value in finding a way and finding a way to look at this from a comprehensive state. But, you know, again, we do research here at the Baker Institute on some plastic waste and policies. And you have to start somewhere. I mean, so we're narrowing the scope and looking at, okay, what are these system impacts? And then also doing research in batteries. And it becomes very, very difficult. And as you know, an LCA practitioner, you know, there's a lack of data and throughout the supply chain too, because it becomes very, very murky once you start exporting and you start tracking and following re-exporting. But there is value to understanding the bigger picture, but you do have to start somewhere, and scoping to certain parts of the life cycle is a good start, and that's what we're doing here.
That's right. I mean, even right now, those models for cross-border trade are contentious, highly limited, and aren't global yet. So one can't build Rome in a day, but certainly it's a wonderful vision to work towards. I'm going to put out to this early question That was actually to all of you, to Rachel, Robert, and Lourdes. General question: as technologists and engineers, how can we help bridge the gap between technology development and policy, both in moving tech from R&D, the R&D bubble, into implementation, but also considering energy justice and social equity? So perhaps we could start with Lourdes, move to Robert, and then end with Rachel on that question. So if you can aim to have, a minute or so answer each, that would be really wonderful. Lourdes, are you there? Oh, you're on mute if you're still there. If you're not still there, I'm going to start passing to Robert. This is, as technologists, engineers, how do we help bridge the gap between technology development and policy, and moving from tech from R&D bubble into implementation, but also considering energy justice and social equity? Robert, and then to Rachel, and then we have some other questions on waste that are coming in. Robert? You're on mute.
Okay, so that's a huge question, and one that has bedeviled energy research and innovation for as long as I've been interested, and I'm sure longer than that. I think perhaps the most difficult point I want to make is that if we need to solve the equity problem within the energy system, we will almost certainly not be able to achieve the scale of transformation that we need to over the coming 3 decades. And we really need to see the equity problem as being something that needs to be solved at the level of the entire society, and not just at the 5 or 10% of the society which is accounted for by energy systems. I hope that makes some sense.
Thank you. Lourdes, if you can provide a brief answer, and then I'm going to try to squeeze in some extra questions for Rachel as well. Thank you, Lourdes, for joining us again. Oh, you're on mute, please. Thank you.
Can you hear me?
Yes, we can.
Oh, okay. That's a really fantastic question, difficult to answer in a nutshell, but I think part of it has to do with first making accessible the knowledge to the common population. I mean, often enough, there is a big gap between all these technological developments and the understanding that people have of them. But also, I think as we are moving towards this paradigm shift that I mentioned, we will need to have more modular, more small scale, and more local technologies. And that's the work of engineers and technicians, technological people who develop this technology, not of the policymakers. So I think we need to make sure that there is this dialogue among ourselves.
Wonderful, thank you. And Rachel, along with that question, I'm now making it even more difficult for you. If you have any thoughts as you wrap up on the transition and R&D, as well as how waste management solutions might apply to nuclear, and what you think are the biggest solutions for solar. I know you only have 1.5 minutes, but whatever thoughts you can bring forward in what time we have left would be wonderful.
Okay, sure. I guess just to address the early question about how to bridge the gap between technology and policy, being in the life cycle assessment field, I like to take that one step further too, by also looking at and organizing laws and regulations with a life cycle framework. And so when we start, when I talk about bridging the gap and closing the gap between the energy sector and the R&D in the early upfront stage with the later on down the supply chain and down towards the end of life. I mean, that's first off very important to get that communication going, but also organizing regulations with that life cycle framework. And so understanding how when we are at the R&D phase and we are innovating, you know, having those conversations about what regulations, you know, how and where are resources extracted, what regulations are in place, and then looking at the midway through the supply chain and end of life supply chain, and going through and understanding what those knowledge gaps and regulatory gaps are in order for something to be you know, commercialized and put out there. I mean, we can't scale good intentions. You really need commercially viable you know, options there. And so understanding what the social technology, the environmental, political setbacks are across the supply chain when something is developed is very important. You know, and I guess this, you know, I'll close with this, is there's some questions about solar waste, and that's why I'm a huge proponent of innovation. You know, I talk a lot and write a lot about some of the things that we don't see in the renewable industries, and that's the waste side. And I'm by no means trying not wanting to discourage that. I think we have to innovate and we have to keep developing, but we also have to understand, you know, what that means from a life cycle perspective. We have to understand truly what sustainability is and understand all of those factors. And it has to be scalable, and that starts with investments and innovations and communication with stakeholders and communication with policymakers in order to understand what some of those barriers are.
So this is partly my fault because I tried to squeeze as much conversation as I could out of this amazing panel. Ju is back, and I'm not going to take up any more time because we're a minute over, but thank you so much to our panelists. It's been a blast, and thank you, and a wonderful time, and back to you, Ju. Thank you so much. Apologies for running over a minute.